Hello, let's talk about the graph traversal algorithms, commonly used ones for various problems. So let's check the background. So three of the common algorithms which we would be discussing are breadth first search or BFS, depth first search DFS, and Dijkstra's for the shortest path search. BFS prioritizes visiting vertices close to the point of origin and uses a queue to add unvisited vertices. So the principle is like first in, first out. So we kind of gradually expanding visited vertices like around the point of origin. We start by adding the origin vertex to the queue. Each step we pop the vertex from the queue and go to the vertices adjacent to it which weren't visited yet, and mark their path length as current length plus 1 and mark them visited and add to the queue. So if the graph is non-weighted, this results in the shortest path found from original vertex to any other vertex. Or it can be just used for just traversal of like finding what's connected component of the graph. And DFS prioritizes vertices adjacent to the current vertex and is typically implemented using the recursion. We start from the origin vertex, each step we mark the current vertex as visited and go to all adjacent vertices which weren't visited yet and call DFS for them. So we're kind of like going to the next vertices in depth before finishing visiting all vertices adjacent to the current vertex. And Dijkstra algorithm can find the shortest path in a weighted graph. We start with the origin vertex. This step we keep the unvisited vertex closer to the visited vertices. This would be origin at the first step. Mark it as visited and declare the shortest path found for it. Then for every edge from it we check if the length of path to it plus the edge weight are shorter than the current length of path to the target vertex and update it if so. The algorithm ends when all vertices are visited or the vertex of interest becomes visited. For complete graphs, we can do like a v-square algorithm works well, where we just have array of current distances to each unvisited vertex, from like unvisited to visited. And then for sparse graph, using a priority queue works better for selecting the unvisited vertex with the shortest path. You can either update elements in the queue or just add new lengths and discard entities which are stale. Time complexity would be e log v, where e is the number of edges. And let's take a look at example. Finding a number of islands. You are given a two-dimensional array n times m with ones and zeros, where 1 denotes land and 0 denotes water. Find a number of islands connected by movement up, down, left, or right. So in this example we have like 4 islands, and the solution would be we just iterate over the array. If the current cell is not visited, start either BFS or DFS from it, marking the connected cells as visited and bumping the counter of islands. So we keep going while the recursion not ends in case of DFS, or while the queue is non-empty in case of BFS. And we need to check edge cases when we are like at the edge of the array. For example, I or j equals to 0, or like equals to n minus 1, m minus 1. Time complexity ends up being O n times m, basically linear from number of elements total. Yeah. So another example is Labyrinth. You're given two-dimensional array n times m with characters. X denotes a wall, dot denotes a regular terrain, and O denotes a difficult terrain requiring twice as long to get into. Find the shortest path from one cell to another. Like in this example, we start from like S, we go up, then right, then down, and right to get to F. In this case, it's pretty simple. So there is like just like pretty much one path. But overall, yeah, treat array cells as graph vertices and movements as like movements by edges with weight 1 or 2 depending on the terrain difficulty. So for example, first step here in this path would be length 1. Second step up would be length 2, then again length 1, and so on. And we just use Dijkstra algorithm to find the shortest path, or like absence of thereof. Let's get to homework. So I recommend you to try to do it yourself first, then like put the video on pause, and then come back for analysis of the problems. that I would be doing. So first problem would be, given a directed graph, find if it has cycles. And second problem, given a weighted tree graph, find the longest path length between any two vertices. And then like third problem, given a directed graph without cycles, output vertices in topologically sorted order. So for every edge uv, u comes before v in this order. So like basically the entries which are like more like on top of the graph appear first, and those are which are like just basically don't have any outgoing edges, they appear the last, and they can be in any order. So let's take a pause. Okay, so let's get to a solution for the first problem. So first approach could be, hey, let's just like start a DFS, and if we encountered some visited vertex from a current vertex, then it means it has cycles. But it would not be very simple, because suppose you have like just simple graph, maybe two vertices. You start from like when you have edge from like vertex 1 to vertex 2. Suppose you started with like vertex 2 first. Then like it would be visited, and when you visit it from 1, it's also gonna seem like visited. But it's not because of a loop, it's because just like order of how we traverse the graph. So instead we're gonna have 3 markers. 0 is not visited at all. 1 is like visited but not exited from. And 2 means visited and exited from. So, and in this example which I was just given, what happens is like we start with vertex 2. It becomes visited 1, and then it becomes visited 2 because we exit from the DFS. And then we basically only declare a cycle if we encounter a vertex which is currently visited 1, but not visited 2. Because visited 1, it means it's a part of the same like DFS attempt, and we just traverse somewhere back to the vertex which we haven't exited yet, which indicates a cycle. But it filters out cases when we just visit some vertices because of different like order in the graph. So second problem. So since it's a tree, it actually doesn't matter much for like weighted and non-weighted solution. They're going to be the same. We're again going to use DFS. So we start from some vertex. It doesn't matter which one. And then like for we do DFS, and then for like every vertex, whatever holds is like either like optimal path traverses from this vertex, or like visit this vertex, or it's somewhere like on top of it, or it's somewhere to the bottom of it in subtrees. So we maintain the answer, and like we first check, hey, what's the like answer for like subtrees, and like check if it's bigger than current one. Then we also maintain what's the like longest path in depth, which starts with a current vertex. And another thing we maintain is like path from length of path from the root. So, and this way, like when we traverse the children of a current vertex, we basically get the longest paths for each of them, and that plus path from the root give us like all the possible paths from the like current vertex, and maybe with exception with the root, because they can be a bit longer paths and if it traverses beyond the root. But it's okay, because like if a path, optimal path, it includes the root, we're gonna like consider it when we like compute the value from the root. So we have a bunch of like sub passes, and we combine them and just like basically pick the two biggest ones and combine them into a single path and compare it with the answer. And yeah, since like we visit every vertex, and like optimal like longest path should come from at least some vertices, then we'll eventually like consider it. And then the last problem, it's like a classical problem, like topological sort. We do DFS, and then when we get out of the vertex, we add it to the array, but just need to do it in the reverse order. Um, and then basically that means that like we like first we would exit from vertices which don't have any like child vertices, and the property is like that for every vertex which has a child vertex, we would essentially exit from that child vertex earlier. Like no matter is it like a part of the same DFS iteration or like a couple of different DFS iterations. So it's gonna hold, so we're gonna get a sum of topological order. Yeah. So I know these problems are mainly focused on DFS, but those are some of the like most interesting ones. Thanks for watching. Let me know if you have any questions.